Good morning. So today we are discussing module 5. Module 5, the sampling theory part of second part of module 5. And the last session we had discussed a little bit of the different terms, the hypothesis, what is first type error, what is second type error, etc. So today we'll discuss the concept of tests of significance and confidence intervals. Tests of significance and confidence intervals. Okay. So the process, the question might come for 1 or 2 marks. Define test of significance. So the process which helps us to decide about the acceptance or the rejection of the hypothesis is called the test of significance. The name itself says the test of significance. So we are studying test of significance and confidence intervals. The process which helps us to decide about the acceptance or the rejection of the hypothesis. So this is a process. Test of significance is a process which helps us to decide about the acceptance or rejection of the hypothesis. It is called the test of significance. It is called as the test of significance. It is called as the test of significance. Okay, let us suppose that we have a normal population. Yes, normal population. Population means the items which are under study here in statistics are called as population. Okay, now let us suppose that we have a normal population with mean mu and standard deviation sigma. With mean mu and standard deviation sigma. If x bar is the sample mean of a random sample, if x bar is the random sample mean of a random sample of size n, if x bar is the sample mean of a random sample of size n, the quantity z is defined by, see the quantity z, new formula is coming. The quantity z defined as x bar mu minus mu divided by sigma by root n. The quantity z defined as x bar minus mu divided by sigma by root n is called standard normal variate. This will come again and again in problems. So standard normal variate z is equal to x bar minus mu divided by sigma by root n. Standard normal variate z is equal to x bar minus mu divided by sigma by root n. Here mu is the mean, sigma is the standard deviation, and x bar is the value of the mean, that is for the x. So mu is the mean of the normal population. Mu is the mean of the normal population. Z is the standard normal variate. N is the random sample of size n. N is the sample size. This is called standard normal variate, or the short form is SNV. Standard normal variate, or the short form is SNV. We can say with 95% confidence. So this is the theory. I'm lightly explaining the theory for you. That's all. For you, the problems are very important. This you should just know. We can say with 95% confidence that Z lies between minus 1.96 and 1.9. You have seen the, just imagine the normal curve, standard normal variate, the bell-shaped curve. So we can say with 95% confidence that Z lies between minus 1.96 to 1.96. So this side 1.96, this side minus 1.96. Further, 5% level of significance is written as Z of 0.05. 5% level of significance means it is written as Z of 0.05. So suppose you take 6%, then it is written as Z of 0.06. So always, most of the time we use only 5% here in your syllabus. Further, 5% level of significance is written as Z of 0.05. Thus we can write by the calculation. For you how the derivation is not needed. We can write Z is in between minus 1.96 and 1.96. So Z value is here. So I wrote it minus 1.96 less than or equal to Z. But the Z value is x bar minus mu by sigma by root n less than or equal to 1.96. Okay. So now simplifying this, if we simplify this, what we get? That is, actually multiplying all of this, then bringing everything to one side, keeping only mu in one side, etc. The derivation, no need for you. Very simple, just multiplying and then keeping only one side. So minus 1 per sigma by root 10. Then mu you want, so x bar that side, like that. So simplifying, we get x bar minus 1.96 sigma by root 10 is less than or equal to mu. That is less than or equal to x bar plus 1.96 sigma by root 10. So from this we get next step, x bar minus 1.96 into sigma by root 10 less than or equal to mu, that is less than or equal to x bar plus 1.96 sigma by root 10. So from the table of normal, I've sent you the table. From the table of normal, 99% of the area lies between minus 2.58 and plus 2.58. Majority of the area lies in that, because it's a bell, the normal curve, normal distribution curve is a bell-shaped curve. So from the table we know that for a normal curve, 99% of the area lies between minus 2.58 and plus 2.58. 99% of the area lies between minus 2.58 and plus 2.58. From the table we know that. It is from the normal table we can make out, and by looking at the curve also you can make out 99% of the area lies between minus 2.58 and plus 2.58. So we can also say from that, by in the same argument, x bar minus 2.58 sigma by root 10 less than or equal to mu less than or equal to x bar plus 2.58 sigma by root 10, that is taken as 3. Now we say that this 2 is the 95% confidence interval and 3 is the 99% confidence interval. Remember, this is an interval now, mu lies between these two. Okay, this 2 is the 95% confidence interval, because the values are 95%. I have told here 95%, we can say with 95% confidence that z lies between. So we can say with 95% confidence that z lies between minus 1.96 and 1 plus 1.96. So this is a 95% confidence interval, equation 2, and 3, that is 99%. Here you similarly from the table, 99% of the area lies between. So this is 95% confidence interval and this is 99% confidence interval. And now see the two curves I have drawn. This is a normal distribution curve. Okay, you know this, no? Normal distribution curve. It is a bell-shaped curve. It is a bell-shaped curve, is it not? Bell-shaped curve, and also you can see here it is minus 1.96 and 1.96 here. Minus 1.96 is here and plus 1.96 is here. So this totally is 95%. The unshaded portion can make out majority. Remaining is 5%. So 2.5% this side, 2.5% this side. So shaded portion. Here also you can see 99%. And it's between minus 2.58 and plus 2.58. So 99% means remaining is 1%. So 0.5%, 0.5%. So the total shaded area 0.05 being, so 0.5, it is actually 0.5. The total shaded area 0.05 being the level of significance of the test. Being the level of significance of the test represents the probability of making type 1 error. Type 1 error. Type 1 error means what? Rejecting the hypothesis when it should have been accepted. So remember that type 1 error means rejecting the hypothesis when it should have been accepted. Type 1 error means rejecting the hypothesis when it should have been accepted. Okay, the total shaded area 0.05 being the level of significance of the test. It is the level of significance of the test, represents the probability of making type 1 error. It represents the probability of making type 1 error. Type 1 error means rejecting the hypothesis when it should have been, so it should have been accepted but we rejected it. Type 1 error means rejecting the hypothesis when it should have been accepted. The set of values of z outside the range. So the set of values of z outside minus 1.96 and plus 1.96 constitutes the insignificant region. That is the main critical region. So remember, the set of values of z outside outside the range, the set of values of z outside the range minus 1.96 and plus 1.96 constitutes the critical region, or it's also called as the significant region. So the set of values of z outside minus 1.96 and plus 1.96 is a significant region or critical region, or the region of rejecting the hypothesis. Significant region means it is the region of rejecting the hypothesis. This will come later. So outside the tail, the ending portion, this is the region of rejecting the hypothesis. That is the region of reject. Significant region or critical region means it is the region of rejecting the hypothesis. It's the region of rejecting the hypothesis. Okay, whereas the values of z within the same range, the value of z, the values of z within the same range constitutes the insignificant region. So outside minus 1.96 and plus 1.9, that's the shaded portion. It is the region of rejecting the hypothesis. That's a critical region. It's the region of rejecting the hypothesis. Whereas the value of z within the same range, minus 1.96 to 1.96, it is the insignificant region, or it is the region of acceptance. Outside is the region of rejecting. The inside is the region of accepting. So outside minus 1.96 to plus 1.96, the region of rejecting. Inside minus 1.96 to plus 1.96 is the region of acceptance of the hypothesis. It is the region of acceptance of the hypothesis. Now one-tailed and two-tailed. This gives rise to the next very important concept, that is one-tailed and two-tailed test. So one-tailed and two-tailed test. So in what it means, so lightly I will just explain. In our test of acceptance, a significant test, in our test of acceptance or non-acceptance, acceptance means we take it, non-acceptance means reject. In our test of acceptance or non-acceptance of a hypothesis, we concentrated on the values of z on both sides of the mean. So we always concentrated in our test of acceptance or non-acceptance of the hypothesis, we concentrated on the value of z on both sides of the mean. So we concentrated on the values of z on both sides of the mean. That is, focus of attention lies in the two tails of the distribution. I told you. So here, this is the region of rejection. This is the region of acceptance. So the focus now will be on the two tails, the end tails. These are called tails. So the focus will now be on the focus of attention lies in the two tails of the distribution, and hence such a test is called a two-tailed test. So see again, if you read this sentence, you can make out. In our test of acceptance or non-acceptance, of a hypothesis, we concentrated on the value of z on both sides of the mean. We concentrated on the values of z on both sides of the mean. That is that side also, this side also. That is, focus of attention lies in the two tails of the distribution. I told outside means rejection, inside means acceptance. So focus of attention lies in the two tails of the distribution, and hence such a test is called a two-tailed test. And so such a test is called a two-tailed test. Sometimes we will be interested in the extreme values to only one side of the mean. So sometimes when studying, you will see later, we will be studying only on one side of the mean, that is one side of the graph. In which case the region of significance will be a region to one side of the distribution. So suppose we consider only one side of the mean. Okay? Suppose we consider only one side of the mean. Then in that case, the region of significance will be the region on one side of the distribution. Suppose we consider only one side of the mean, that is one side of the mean is in the middle, one side of the graph. Then the region of significance, will be the region on one side of the distribution. The region of significance will be a region on one side of the distribution. It will be a region on one side of the distribution. Then the region of, suppose we concentrate on only one side of the mean, then the region of significance will be a region on one side of the distribution. So hence the area of such a region will be equal to the level of significance itself. So we can say the area of such a region is equal to the level of significance itself. The area of such a region will be equal to the level of significance itself. Such a test is called a one-tailed test. So if you concentrate on only one side of the region, then the region of significance will fall on one side of the distribution. The region of significance will be a region to one side of the distribution. Hence, the area of such a region, the area which is concentrated on one side of the region, the area of such a region will be equal to the level of significance itself. The area of such a region will be equal to the level of significance itself. Such a test is called a one-tailed test. Such a test is called a one-tailed test. Okay. Now this table you have to remember so that you will understand the problems and you will be able to solve the problems. The following table will be useful for working problems. Just see here. Test. First column is test. Second column is critical values of z. First column is test. Second column is critical values of z. In this critical values of z, there are two parts, 5% level and 1% level. In this critical level of z, there are two parts, 5% level and 1% level. So again I repeat, the following table which I am discussing now will be useful for solving the problems. Will be useful for solving the problems. Okay. So the table, first column is test. So there are two tests, one-tailed test, two-tailed test. And then critical values of z, that is 5% level and 1% level. Critical values of z, there are two types, 5% level, 1% level. So one-tailed test means for 5% level, the critical values of z lies between minus 1.645 or 1.645. 1% level lies in between minus 2.33 or 2.33. Similarly, for two-tailed test, the critical values of z at 5% level falls in between minus 1.96 and 1.96. And for 1% level, it falls in between minus 2.58 and minus 2.58 and 2.58, minus 2.58 and 2.58. Okay. Now here you can see minus 2.58 and 2.58. Okay. Now tests of significance for large samples. So we come to the part where test of significance for large samples. So different types of tests, large samples, small samples, proportional. In the tests of significance for large samples, you are having the test of significance of the proportion. In test of significance for large samples, you are studying, there are many types in that. First you are studying test of significance of proportions, how to solve the problems in this. So in this test of significance for proportion, P means probability of success, Q means probability of failure. P means probability of success, Q means probability of failure. So P plus Q is 1. You can remember the binomial or Bernoulli distribution. So test of significance for large samples. So in this test of significance of proportion, so P means probability of success, Q means probability of failure, P plus Q equals 1. Here binomial distribution is regarded as the sampling distribution. So here you can make out binomial distribution is regarded as the sampling distribution of the number of successes in the sample. Here binomial distribution is regarded as the sampling distribution of the number of successes in the sample. Here binomial distribution is regarded as the sampling distribution of the number of successes in the sample. So mean of the distribution, since it is a binomial distribution, mean of the distribution is NP. Since it's a binomial distribution, mean of the distribution is NP. So standard deviation will be standard deviation equals square root of NPQ. Mean of the distribution is NP. Standard deviation will be square of NPQ. Mean proportion of success. So the mean proportion of success will be NP by N. So the mean proportion of success will be NP by N, that is equal to P. Standard deviation or standard error. Standard deviation or standard error proportion of success. SD means standard deviation. SE means standard error. So standard deviation or standard error proportion of success is given by square root of NPQ divided by N. That is NN get cancels, and we can, here root n is there, n can be written as root n into root n, so 1 root n get cancelled, so you can write root pq by root n, that is root of pq by n. So standard deviation or standard error proportion of success is given by square root of pq by n. Now let x be the observed number of successes in a sample. Let x be the observed number of successes in a sample. Let x be the observed number of successes in a sample size of n. Let x be the observed number of successes in a sample size of n, and mu equals np be the expected number of successes, and mu equals np be the expected number of successes. Then associated standard normal variate z is defined by associated standard normal variate. It came before also. Z is given by z equals x minus mu by sigma. So mu is np, sigma is root npq, so x minus np by root npq. Okay. The associated standard normal variate z is given by x minus mu by sigma. Mu is np and sigma is root npq. So z will be x minus np by root npq. X minus np by root npq. Okay. Now, if mod z is greater than 2.58, that meaning is z is in between minus 2.58 and plus 2.58. If mod z is greater than 2.58, we conclude that the difference is highly significant. If mod z is greater than 2.58, we conclude that the difference is highly significant and reject the hypothesis. Understand this. If mod z is greater than 2.58, we conclude that the difference is highly significant. If mod z greater than 2.58, we conclude that the difference is highly significant and therefore we reject the hypothesis. So again I repeat, if mod z is greater than 2.58, that is z value is in between minus 2.58 and plus 2.58, we conclude that the difference is highly significant and reject the hypothesis. We conclude that the difference is highly significant and then we reject the hypothesis. Since p is the probability of success, since p is the probability of success and square root of pq by n is the standard error proportion of success, we say p is equal to plus or minus 2.58. P is equal to plus or minus 2.58, plus or minus 2.58 square root of pq by n are the probable limits. P is equal to plus or minus 2.58 square root of pq by n are the probable limits. Okay. So now this much is there, and I will continue this. In lot of theory is there, and this again 1 or 2 class is complete theory. Then I will start the problems. So once the problem starts, then within 1 or 2 classes we can end this module, end of the syllabus. So once again, because there is time, I'll just roughly go through this. So test of significance and confidence intervals, the process which helps us to decide about the acceptance or rejection of the hypothesis. The process which helps us to decide about the acceptance or rejection of the hypothesis is called as the test of significance. It is called as the test of significance. Okay. Let us suppose that we have a normal population with mean mu and standard deviation sigma. If x bar is the sample mean of a random sample of size n, the quantity z is equal to x bar minus mu by sigma by root n, that is taken as equation 1 here, is called as the standard normal variate. It is called as the standard normal variate. So we can say with 95% confidence that z lies between minus 1.96 and plus 1.96. I'll show the figure later. We can say with 95% confidence that z lies in between minus 1.96 and plus 1.96. Further, the 5% level of significance is denoted by z of 0.05. Thus we write the z lies in between minus 1.96 and 1.96. So we can write in place of z here minus 1.96 and plus 1.96. Minus 1.96 less than or equal to x bar minus mu by sigma by root n less than or equal to 1.96. Okay. Simplifying this, multiplying and all this you know. So x minus 1.96 sigma by root n less than or equal to mu less than or equal to x bar plus 1.96 sigma by root n. I'll take it as equation 2. Similarly, from the table of normal distribution, table of normal distribution I sent to you, and also the normal distribution table is the graph is a bell-shaped curve. 99% of the area lies between minus 2.58 and plus 2.58. So we can say x bar minus 2.58 sigma by root 10 less than or equal to mu. That's the area. Less than or equal to x bar plus 2.58 sigma by root 10. It is taken as 3. Now we say that 2 is the 95% confidence interval. This 2 is called as, because 95% it is correct. We can say with confidence 95% that the z value lies in between minus 1.96 and plus 1.96. So we say that equation 2 is called as 95% confidence interval, and equation 3 is called as 99% confidence interval, because from the table of normal you can say that 99% we are sure to say that the area lies between minus 2.58 and plus 2.58. Yeah. Now the two curves you can see here. See the normal shaped curve, normal distribution curve. So 1.96 and minus 1.96 plus 1.95%, remaining 5%, 2.5%, 2.5%. So here also 99%, remaining 1%, 0.5% and 0.5%. So the total shaded area 0.05 being the level of significance of the test. It is the level of significance of the test. It represents the probability of making type 1 error. It represents the probability of making type 1 error. Okay. 2.5 plus 2.5 is 5%. 5% means the total shaded area 0.05 here. This and this total shaded area 0.05. It is the level of significance, being the level of significance of the test. It represents the probability of making type 1 error. Represents the probability of making type 1 error. What is a type 1 error? Yesterday in the last session I have discussed rejecting the hypothesis when it should have been accepted. That is called type 1 error. The set of values of z outside the range minus, that means this side shaded portion, constitutes the critical region. Outside the range minus 1.96 plus 1.96 constitutes the critical region, or the region of rejecting the hypothesis outside. So it's a tail. Whereas the value of z within the value of z within the same range constitutes the insignificant region. Value of z within the same range constitutes the insignificant region, or the region of acceptance. So outside is the region of rejection. Within it is the region of acceptance of the hypothesis. So we come to the, because it is concentrating in the tails. So one-tailed and two-tailed test. Test of acceptance or non-acceptance of the hypothesis. We concentrated on the value of z on both sides of the mean. Mean is in the middle. That is, focus of attention lies on the two tails of the distribution, endpoints. And I have shaded it. You can see the diagram. And hence such a test is called a two-tailed test. Hence such a test is called a two-tailed test. Okay, such a test is called a two-tailed test. So it's concentrating on the tail, so it is called as a two-tailed test. So now, sometimes we will be interested in the extreme values to only one side of the mean. Sometimes you are concentrating only on one side of the mean, in which case the region of significance will be region to one side of the distribution. Hence, the area of such a region is equal to the level of significance itself. Such a test is called on one side we concentrate, hence the area of the region will be equal to the level of significance itself. Such a test is called a one-tailed test. Such a test is called a one-tailed test. So the following table is useful for working out problems. You can see here one-tailed test means the critical values of z. 5% level means in one-tailed test the value of z lies between minus 1.645 or plus 1.645. And 1% level means critical value of z lies between minus 2.33 or 2.33. Okay, coming to two-tailed test, critical values of z 5% level lies between minus 1.96 and plus 1.96, and 1% level critical values of z lies between minus 2.58 and 2.58. It is clear. Now the tests of significance of large sample. There are 3 or 4. Today I will be discussing one. Test of significance of proportion. P is the probability of success, Q is the probability of failure, P plus Q is 1. So this is somewhat like the first starting in module 4, binomial distribution or Bernoulli distribution. So here mean is NP, standard deviation is square root of NPQ. Mean proportion of success is NP by N. Mean proportion of success, mean divided by total number of elements in the sample, so that is P. standard deviation or standard error proportion of success is square root of npq by n. So n can be written as root n into root n, so it will be root pq by n. Let x be the observed number of successes in a sample size of n, mu equals np be the expected number of successes. Then associated standard normal variate z is given by x minus mu by sigma, mu is np, sigma is root npq. Okay. Now if mod z, this is a very important statement, if mod z greater than 2.58, mod z greater than 2.58, we conclude that the difference is highly significant. If mod z greater than 2.58, we conclude that the difference is highly significant and reject the hypothesis. Understand that, remember it. If mod z greater than 2.58, we conclude that the difference is highly significant and we reject the hypothesis, since P is the probability of success and square root of PQ by N is the standard error proportion of success. So P plus or minus 2.58 root PQ by N are the possible limits. Once again, if mod Z greater than 2.5, we conclude that the difference is highly significant and we reject the hypothesis. Difference is highly significant and we reject the hypothesis. This will be used in problems later. Since P is the probability of success and root PQ by N is the standard error proportion of success, yes, now I found out here, see, root PQ by N, root PQ by N. So P plus or minus 2.58 root PQ by N are the probable limits of this. P plus or minus, derivation no need, plus or minus 2.5 root PQ by N are the probable limits for this. So time up. So there are about two classes I need to finish the theory, lot of theory, the chi-square test, goodness of fit test, and you need to know all the theories. So then I might need 1 or 2 classes to solve the problems, okay? So once again, I remember you, every time I'm remembering you, write the notes, complete it, I'm going to check it and finish assignment 1 and be ready for the exams. Clear? So I wind up the session. All the best. Thank you.